Okay, I'm not recording this on my normal computer because I don't really need to write anything on the screen or anything for this here. I just want to kind of go through this midterm, and I can just verbally give you the answers for each of the questions here. There. Okay, question 1. What are the major differences between a microprocessor and microcontroller? Okay, microprocessor is a general purpose processor. It contains no RAM, ROM, serial ports, I/O ports. The clock generator is usually not built onto it. It requires a crystal or an external clock generator. Doesn't have any timers. Does not have any watchdog timer. None of that is built into it. A microcontroller contains a small microprocessor along with some or all of those things that I mentioned: RAM, ROM, timers, watchdog timer, general purpose I/O chips, sometimes analog to digital ports, sometimes digital to analog ports. Actually, yeah, some of them will have both there. Watchdog timer is built in. Internal clocks can sometimes be built in. Typically, one other major difference is a microprocessor is normally a much more powerful device than a microcontroller. A microcontroller is usually a very small microprocessor. So, again, you need to put that in your own words on the final exam. Give an example where you would use a microprocessor. Obvious place, a desktop computer. Less obvious, the aircraft on a 747, 777, a large aircraft cockpit would contain typically a large full-blown microprocessor as the cockpit controller. At there, you would find microprocessors quite often used in large hospital equipment, CAT scans, MRI machines, anything that requires a lot of processing. Some video game consoles will use a microprocessor. Some will use a dedicated microprocessor, which is more like a microcontroller. An example where you would use a microcontroller. A microcontroller would be used in a refrigerator, a coffee maker, the engine controller on your automobile, the CD player or DVD player in your home. It would probably control most modern televisions. Your keyboard would probably have a microcontroller. Possibly your mouse would have a microcontroller there. So you would list a series of these. The main difference you want to keep in mind that a microprocessor is typically for a much larger system and usually a multitasking system. Microcontrollers are used in a single purpose application. That also helps for problem part A. Okay, how many different memory spaces are there in the 8051 microcontroller? The answer is 3. Let me go back to, hopefully I can find it quickly. Right there, I'm trying to think where it's at. Hold on, let me pause my thing to where I can find it here. Okay, I'm going to resume, and as we look at our system overview of the 8051, these are the slides. I posted this up on Facebook. That's where I got these from, right there. So, close that, and we will close that. And as we look at this here, it wasn't in this slide, right here, this set of slides, so it has to be in another set of slides. I'm going to just probably minimize that. System overview, right here. Okay, this slide right here is the answer to that question. There are 3 program memories. There are 3 memories. One is program / data memory. That's in flash. Again, that's built onto the chip. Then we've got our data memory. Then we got our external address spaces. Now these use 3 different commands. You would use move C if you're going to use program data memory. You would use just move there, and then you would use move X. Now let's go back to our quiz question here. This is how many different memory addressing spaces there are. There are 3. What are they? Code, or program memory, data memory, or there, and again we look at this right here, data memory, program memory, or code, and the other is external. What is each used for? Program memory is where your code is downloaded into it. That's your code. Your data memory is your general purpose RAM. Some of that is used, and I will be looking for that, for the special function registers. If you look back at this slide here, right here, you will see that our special function registers will contain the upper 128 bytes of the internal data memory. Also inside our external memory, we've also gotten 32 bits that are reserved for our special function registers right there. Excuse me, there's a fan on in my office here at home. Got there. So, going back to our question, right there, the answer there is there are three. What are they? Program, data, and external. What are they used for? Program is obviously where your program is used for. Your data memory is multi-purpose. It has three different purposes. One is you've got some space for general scratch pad RAM for just using memory. We use that for when we were doing our adding. Also in the data memory, we have our 4 banks of our R0 through R7. We only used 1 bank in our class, but you can have 4 banks. And then your special function registers. Your external memory is used for any applications that requires more memory than what's available in the data memory, and it can be used for whatever. It's just usable RAM for whatever. And you should also note that that is also internal. Some of that is internal to our 8051. Give the direct memory addressing modes used in the 8051. That came straight from the slide right there. As we look at our instruction set, right there, we have a slide here that gives, there's our, and let me minimize that one there. The question is what are the different memory addressing methods used in the 8051 given at an example each? Right here is what you need to use for that answer. There's 8 modes. The register, direct, indirect, immediate, constant, relative, absolute, long, and index. Those are the 8. You need to know those. Right there. Next question is what instruction would you use to move the number 03E to 30? That I will just type that there. That is move to 30H 03EH right there. There. The next one is move to X. It's external memory. And here we have our location, which is a 16-bit location right there. I could put an extra 0 there to show that's a 16-bit location. And that is the number 0, the immediate number. And actually, I forgot that 02EX. We also need to have here the number sign for the immediate, to show that we're going to move the immediate data 03E in the location. So that's problem 2, or problem 1. Problem 2 is what effect does the power selection have on the clock power consumption? Simple. You double the power, you quadruple the power consumption. That there. It is a exponential growth in power consumption there. So, speed up, power consumption, up, right there. Hang on, that there. List at least 2 reasons you would want to use an external clock instead of the one in there. One reason is the internal clock is only accurate to plus minus 20%. You need a more accurate clock. Right there. 2 is you need, and again, there's multiple reasons, I'm just giving 2. 2 is you need to synchronize, and that's misspelled, but we have, we'll just use sync, multiple processors with one clock. A third reason may be you want to use a very low frequency to save power. Right there. So I gave you three that there. So list at least 2 reasons why you want to use an external clock. The purpose of Watchdog Timer, to reset the processor in the event of a software lockup or hardware failure. You're right there. Examples right there, and you can have many examples. One is, jet engine controller. That's an obvious one. A heart pacemaker. Somebody puts somebody's heart. A petrol pump controller. Any type of vehicle control right there. And we could have many examples there. Out there. Just give an example I'm looking for. What are the instructions? Those instructions were also in the slides right there. Right there. They came from the system clock and the crossbar. Right here. And we find it right here. Right here is in C, but again, I'm just going to copy this. The answers in here would be, up there, I would just simply say, I'm just going to right there. I'm just going to convert them, move, right there. I'm just converting them to assembly language versus C. Right there. Those are the 2 commands. Again, they come from this discussion right here, where to disable the Watchdog Timer, somewhere it says right here. Yeah. There. Okay. Writing followed both enables and reloads Watchdog Timer, writing 0 DE file within 4 clock cycles that they're disabled. So that's the command for doing that. The purpose of the priority crossbar encoder, again, that comes from this discussion right here. And the crossbar right there is, here are the problem available, there are a limited number. This is the purpose right here. Right here. This is the answer to this problem right here. Copy that right there. Right there. So again, the issue is that we've got far more pins available. These are all the various. This particular chip's got 32 pins. We've got, you can use them as general purpose I/O, or we can use them for a serial port. This is another port. We can use them for analog. We can use them for all kinds of various things, depending on what we want there. So again, the solution is right here. The answer to that question, right there. Copy that. And I'm just going to put that down right there. So that is the answer to that question. Is it assigns the pins on the outside of the microcontroller to whatever peripherals we want to use internal. We pick and choose what peripherals are necessary for application and only assign those to external pins. That is the function of the crossbar. So whenever you design a system, you decide if you're going to use a serial port or if you're not going to use a serial port, then don't take those pins out. Just simply leave them alone. That there. Okay. Problem 3. A nested subroutine. I'm just going to type the answer to that right there. It's a subroutine contained completely within another subroutine. And you should have seen this in your C class right there. Last in, first out. Used for stack operations. Right there. Replace the micro. I'm going to just use the word micro. It could be micro P or microcontroller. Returns to after an interrupt or subroutine call. Right there. What is the purpose of the stack? The stack contains the return, the contents of all the registers and return address. So it's not to take the stack. So the micro can resume operation at the end of the interrupt. Remember my example of the nurse that put her page in the book. There. What's the advantage of using interrupts? All right, we go back to our slides. That one is also answered in our slide. Right there. And actually, I think it was a different set of slides I used. Right there. It might have been interrupts. Here we went through the interrupt slides. Right there, and that there. And somewhere in here, disabling, next order. We didn't go through a lot of these, but, and I'm not sure how much I went through this. I went through a series there, but this is the answer we're looking for. An interrupt is a occurrence that causes a suspension, are important because they allow a system to respond asynchronously and deal on the middle that there. It also gives the illusion. So these are right there, copy. That would be the answer that I'm looking for right here. What are the advantages of using interrupts? I'm just going to paste that right there. Right there. All right, polling we didn't really talk about, but polling, and I don't, as I recall, that may not be on the test, but let me just give the answer. That polling is that we're just constantly monitoring right there, is it just simply uses less memory right there. The two differences, that's fairly easy. I'm not going to go explain it. A maskable can be ignored. Well, I'll just say maskable interrupt can be ignored, whereas a non-maskable can. All right. Interrupt service routine, that is again given in our slides here. So a routine that deals with that is called the interrupt service routine. Right there. It performs the desired operation turn. So this slide right here is the answer that we're looking for right here. So again, most of this test is coming from the slides right there. So paste. Right there. Right there. This one really, we didn't really get into, but I'll just leave that there. Outline the process that is called when a subroutine that occurs. That I told you in class very clearly is this slide right here. You need to know what happens during this process right there. So, again, you probably should just memorize this. Copy that right there. That would be the answer you would expect. Okay. I'm not going to go through the calculations on this. I'll let you get there. Explain the function of this program. This is a relatively short program here. Up there is a function of this. This is Blinky. Blinky turns on, off an LED. LED at certain time intervals. Right there. What does that there? Subtracts 1 from R5 and keeps. Now, my computer is doing funky things. And where's my grid lines? Oh, my grid line ruler. Turns at certain time intervals. Okay. And stays put, stays where it's at. In other words, it just keeps repeating that and repeats. And I don't know why I'm not allowed to type that there. You know, my keyboard seems to be working. Okay. All right. What does the complement green LED do? If it's on, it turns it off. If it's on, it turns it off. This one here, I misspelled that between events. That one is the one you have to do the calculation. I'm not going to go through that there. I'll let you get there. But basically, you take the two. Well, let me just kind of start it here. Is that if we look at our code here, it does it 3 times, right? So we've got 256 times 256 meaning 65,000 there. Our clock frequency is 2 megahertz. We divided that by 3 and then by 2 in order to get the frequency that there, 2 megahertz right there, divided by, was it what, 12 that there. We go back to our timing discussion right there. Where's our timing instruction? I don't know if this gives us our timing, the timing pattern or not. That I think I had to go through another set of slides, and I didn't really go. This was just the instruction set right there. Our timing is not in here. Where is our timing? It should be in those slides, but programming system overview. No, this particular set of slides did not do that. I gave you a web page to go through and look at the timing right there. And where was it? Right there, chip delay. All right, we go back to right here, and this is where you're going to look at that there. It's divided by 12, and then there's the jump not zero. It takes 2 machine cycles. So as we look at this right here, the time to execute this is 2 times that there. Now again, we got to change the frequency right there. So this frequency is going to be off a little bit that there. So we look at our calculations right here. So I'm going to use this right there. Divide by 12 equals right there. So that's our machine cycle. We take our 1 over x right there. That's our machine cycle. And then we're going to come up with the fact that this is going to take 2 machine cycles times 2 equals right there times our 256 times 256 equals, and then we multiply that times 3, and that says that it's going to be about 2.35 seconds right there if you go through that process right there. So going back to our test there, that is our time between events right there with a 2 megahertz clock. To change the time to twice a second, well, actually in this particular case you won't change it much, because if we go back and look at our calculator right there, if we divided by 3 and we did this by 2, that's going to be 1.5 seconds. So really, that's a bad question right there. So again, but that's how you would do it right there. You would change that right there. Okay, this one here is, I did not go through this. I write a short program that assumes that 2 inputs are tied that there, and you don't really need to set up the ports for this that there. All we're going to do is we're just going to right there. Matter of fact, I'm going to pause, and I'm just going to, I've already wrote this out. I'm going to just go ahead and explain to it that there, right, two inputs right there. That assumes 2 inputs, hot and cold, and the output for the air conditioner is on that there. So all we're going to do is just constantly read this right here, and we're going to just go into a loop right there and just keep reading this right here. And matter of fact, it'd be fairly easy right there. We would just simply check a bit. Let's go back and look at our instruction set again. Right there, instruction set. Now remember that we can look at, do a jump bit right there. Jump not zero, jump compare, jump zero. We have all these various things here, Boolean operation. We can AND a bit, we can set a bit. See here, we got a jump, no, not zero right there. wait till timer overflows. So in this particular case, we want to look at jump if a specific bit is not set or set right there. So we've got jump bit and jump not bit. So we can use those commands to write this code right here. So we can just start right off here, and we can just simply start our code right there, and I'm just going to just write this short little portion that's there. And we're going to look here. If it's hot, we want to turn on the air conditioning right there. So jump not bit, no AC right there. And let's make sure we get the right format. Right there. Right here. See, jump. You know, we look at the bit first. This is a little tricky right here. And we're going to be looking at the hot, and the hot is tied to port 1.0. Jump not set. Here we're going to set. And again, we're going to just look here at the instructions. Now you won't have the instructions available to you, but keep in mind that I will be very generous on this here. Is that as we look at these instructions, we've got our instructions for setting our bits right there. Arithmetic, data transfer. Right here, we've got our add bits, decrement. We've used those in the past, but I want to just make sure show you where you see them right there. And or jump not set. Well, here's our set bit right there. Set bit, and we should have a complement bit. There should be a clear bit right there, clear. So set bit. So you need to know those commands here. Set bit. Set bit. Make sure I did that right. Set bit. Right there. Port 1.7 right there. And this is now jump. Oh, I forgot to put jump. No AC. Right here is no AC. Right here, jump. No bit. We're going to look at the cold. Right there, jump bit. And we're going to look at cold. Right there, that's 1.1. Leave AC on right there. Here, at this particular case, we're going to clear port 1.17 and leave AC on. And I probably should have given more room here. And this is, by the way, this particular question is meant to be harder than the others. And when I normally teach this class, I've taught this class in the past, I would require this question right here, and this is a long jump to start right there. It doesn't have to be a long jump. And that's it. That something very simple like that right there. So again, all we're looking for is a short little program that zooms, and we're going to look at those bits, and then we're going to either clear or set right there. So that's what I'm going to be looking at. So with that said, I'm going to go ahead and post this.